So I'm going to talk about how we process more than 100 billion events a day at Gambia. And I'm going to talk about the current architecture and what challenges we faced, our roadmap on how to improve those pipelines, and then I will answer some questions. So a bit about me. I'm Maxime Ney from France. I've been at Gambia for 5 years. And I'm the lead data engineer, and I've been lead data engineer for the past 2 years. A bit about Gam. We're 250 people. We work with most of the Fortune 100 companies. So companies like Disney, companies like L'Oreal, all those things. And we also work with big websites like Time.com or Rolling Stone, The Atlantic, like very premium publishers. We have offices in 4 different continents, and we've been growing pretty rapidly over the past 6 years. And we recently announced $100 million in revenue last year. So it's a pretty big milestone for us. To give you a bit of context about what we do, we have computer vision tech that we apply to different advertising or marketing use cases. The original one was mostly ad tech. We started about 8 years ago doing what we call in-image advertising, which consists on displaying ads there at the bottom of an image. Then we extended that to many other different ad units. And then leveraging the computer vision tech what we built for this, we introduced this tool that monitors sports sponsorship valuation. So what it does, it looks at social posts and broadcast data. It tries to locate the logos on people's jersey, on the arena, and tries to understand what's the value of those placements for the advertiser, so they can better understand how much they should spend. And very similar, we have a tool that detects the presence of brands in social media in general. So we can give reports to advertisers about what people are thinking about their brand and what's the trend, if people are sharing more about their brands, or things like this. So most of the data that we get is from the advertising business. That can be a bit surprising since we also monitor social medias, but we actually get way more data from our advertising business than we can get from social media. Like in social media, you maybe get a few 100 million posts a day, right? In advertising, you get 100 million. And why is that? Is because every time you open a browser, there is something that's going to happen in the backend, and it's going to request ads to all sorts of different partners. And basically, a single page loading will trigger many events, many requests for an ad. And then in turn, they also generate other things in the backend, like auctions and things like this. So the data that we deal with is in JSON format or in Avro format. So I put some JSON format so you can see a bit what it is. There's stuff like user agent, there's stuff with keywords about the page, stuff like the IP address of the visitor, its location, like all sorts of things like this. So the goal of this data is then to be aggregated and exposed to our customers or exposed to our internal teams so they can optimize and track revenue and all those things. So I was saying, like, a single browser impression can trigger what we call an auction, and that's in the real-time bidding protocol, right? So you trigger an auction. What an auction is basically you have a placement on a page, and it says, okay, how much are you guys willing to spend to put an ad there? So it triggers things called bid requests to different partners. You can have as many partners as you want. In our case, sometimes we have 3 partners, sometimes we have 20 partners. Depends on every impression. Each of those partners can reply with a bid or not. And then based on the bid, you decide whose ad you're going to show, and then you serve the ad there. So a single page load can trigger potentially 1 auction event, n bid requests, n bids, and then 1 impression. So that's really like why we get so much data. So that's the quick numbers in terms of what kind of data we get. It fluctuates a lot depending on so this is per hour, number of auctions we get per hour. So at night it goes to like 1 billion, but during the day it goes to 5 billion, something like this. It fluctuates a lot also in terms of throughout the year. In advertising, it seems like at the end of the year, most of the budget is exhausted, so it dips all of a sudden, and in Q1 it goes back up. And also from during the weekdays and during the weekend, there's a big, I guess, drop in terms of number of impressions that we get. So that's like a snapshot of.
It's very interesting because I work in e-commerce, and you'd think that I get it at the end of the year. Especially towards November or whatever, okay, this is basically the last quarter, I'm seeing, right? So it's going up, but you think you'd want to capture dollars from people getting cash for Christmas.
I guess most of it is spent there.
No, it goes down after 24th.
Yeah.
Up to 24th it keeps going.
Yeah, because no one's going to buy things, but
yeah.
I guess, I wonder what January looks like.
It goes like something like that, at that level, something like that. Q4 is always the biggest quarter.
Sure.
And January is usually half of Q4.
Yeah.
So yeah, it fluctuates a lot. So I'm going to talk about the challenges to process this data. First is the volume, right? That's 50 terabytes of data a day, hundreds of billions of different events. Challenge is also to process and expose that in real time. We do a lot of optimizations based on how ad performs on certain pages, on certain images, on certain keywords, things like this. So it needs to be to have a latency of about 10 seconds. And it's also for ops teams, like when someone turns on an ad, they want to see it serve or not serve right away. They don't want to have to wait like 3 hours and realize we have targeted the wrong demographic or something. And then traffic fluctuates a lot. As we saw earlier, you can have peaks of traffic at a few million events per second, and then it can go down to 500,000 per second. So you have to be flexible enough to handle this kind of load without wasting too much rent, basically. So let's see the architecture. That's the big picture. For those who are familiar with data engineering, here you can see that there's a Lambda architecture. This is the batch pipeline, and this is the real-time pipeline. Everything is in AWS, so all those clusters are deployed in AWS. And basically what happens is all the data is produced from ad server, and then needs to end up in those analytics systems. So that's a custom dashboard that we have, or custom internal tools, and external tools as well for clients. Looker, which is a BI tool, and Amazon Athena for ad hoc queries for BI team. So let's go into more details into those pipelines. So I will first go through the batch pipeline. The batch pipeline, the data is produced in Avro for the most of our traffic. Some smaller, kinds of events are still in JSON because it doesn't really matter. But basically, we use Avro here to improve deserialization time and reduce the volume of the data. Because when you deal with 50 terabytes of data, if you can compress it by 30%, that results in huge cost savings, right? So that's why we chose Avro. And then this data is being produced to 2 different systems. One is called Fluentd, and one is called Kafka. And the role of those 2 systems is identical. They both want to put data in S3, but they act as a backup. Basically, if Kafka is down, then you still have your data in Fluentd that's being uploaded to S3. Now, why don't we use 2 different Kafka clusters? Because that could work too in terms of operational failures, but what we're worried about is someone introducing a bug in that server, and let's say misconfiguring a Kafka producer. And then in that case, you'll end up messing up both arrows and you will lose data. So this way we're kind of separating the code and the operation, and having those 2 completely different pipelines to make sure that we never lose data. Then after this data gets into S3, we use AWS data pipeline to schedule Spark activities. So Spark every hour.
So you're doubling the data in S3, and then it should be identical, right? Because you're saying that Fluentd and Kafka are both creating an S3 file for the same data,
Yes.
so it should be roughly identical.
But
It
it is identical, so we can also actually measure that and figure out that there is not much difference between them. That means everything is all right.
Yeah, okay.
So
Which do you prefer between the two if you had to go with one?
If you're using Kafka and you're comfortable using Kafka, then Kafka is probably a better option for you. If you don't use Kafka, Fluentd is very easy to set up. So
Now also there's different motive behind Kafka. Kafka supports real-time pulling data, whereas Fluentd is just files. So Fluentd can only be used in batch pipeline.
Okay.
that's what I'm saying. So if you're using Kafka for real-time pipeline, then you can just have a separate consumer that puts data in S3 and then have stored consumer.
So yeah, less features but easier to maintain.
Correct.
Yeah, and also the goal of those two pipelines is that one is considered the primary one and one is considered the secondary one. So what it means is whenever we want to do a production change, we're going to first apply it to the secondary pipeline. Every hour when this runs, we have scripts that compare the data output of those two pipelines. And if it doesn't match, it throws an error or it sends email or PagerDuty or whatever. And that way we can first test our code on like production data and in real conditions for a few days or for a few hours, depends how critical the change is. And then we can promote it to primary. So then once it's being processed by Spark, it goes back in Parquet format in S3, so it can be read by Athena or Redshift Spectrum. Some of the data goes directly to Redshift, and some of the data goes to Druid. So that's the three, I guess, different storage layer that we have for batch pipeline.
So on that slide, you have Fluentd, which sends data to S3.
Yeah.
Is your ad servers there? They have the client for Kafka configured inside the app, and they're pushing data to Kafka.
Yeah.
Could you also have the Fluentd just send data to Kafka directly as well? And then you want to have the client.
Fluentd is a passive receiver.
Okay.
So there's no piece of code there which can forward data to some other system.
Oh.
So it's just a server where you can just keep putting data in.
Yeah.
And then it writes it into files, and then it uploads files to S3.
Yeah, I know, but the goal of this is that it's completely isolated. So if you have a misconfiguration in Fluentd or Kafka, you don't have to worry about losing data or something like this. So that's why it's like you wouldn't want to like first only send it to Fluentd and then send it to Kafka, because if these links break, then you lose your data.
Also, the Fluentd is not on the actual box. It's not on.
No.
There is an agent. There is an agent that runs there and that sends data to a Fluentd aggregator, which receives the data and uploads it to S3.
And the Parquet file that is getting generated, like, is that getting compacted into bigger Parquet files, or is it just small chunks of Parquet files?
It's it runs. I think Amazon recommends to use Parquet files of the size of 256 megabytes, something like this, and that's when it's the most efficient. So yeah, so it's larger files. It's aggregated into larger files.
Okay, so you're running some kind of compaction pipeline.
Yeah, this is aggregating things.
Okay.
Yeah.
When do you reconcile between the two, the Fluentd and the Kafka data? Is that part of the Spark job, is to reconcile the two?
So here everything's orchestrated by data pipeline, and in data pipeline you can run scripts or custom code or whatever. So after the Spark jobs, you can say, okay, then run this activity, but it's going to be a script that checks like the output of this job.
Actually, you're not saying the both pipelines here, because he's just talking about batch pipeline right now.
Yeah.
But later on, he's going to talk the real-time pipeline, and then what we reconcile is between both of those.
No, we also do those two things, right? There's two batch pipeline and then one real time.
Oh, I
we
see.
reconcile between the three, but here,
makes sense.
yeah.
Because we were working with Databricks, and we were finding some issues with compacting. The Spark was not giving the feature right in its API to compact small files into one right away, and we had to create separate compact pipelines. So does AWS Spark gives the ability to compact your small Parquet files into one easily, or does it there's some complicated stuff you have to manage?
It's not like AWS Spark, it's like open source Spark, but they just give you.
Okay.
They don't have like a custom Spark version. Well, I mean, they can do, but it's like the same as the open source one. But I think compacting your file is just a matter of changing the number of partitions during your job. So if you have less partitions, it will move bigger files, kind of things like this. So issues we got with this batch pipeline now. The main one is scheduling. When you have like all those activities and all those jobs running every hour, and some of those jobs can contact external databases like Cassandra, or even some of them put data in Redshift, right? So if you have a lot of activities that are running at the same time and interact with the same cluster, you can put a lot of pressures on the systems. Making sure that those activities don't run at the same time is kind of challenging sometimes, especially if they need to run every hour. So one solution for that is to have a separate cluster dedicated to analytics. So for example, in the case of Cassandra, we have our ad server that reads data and push data to Cassandra. And all this data in this Cassandra cluster is being replicated to a different Cassandra cluster that's dedicated to analytics. And all jobs only interact with this analytics cluster. So in case, like, I don't know, we start like 5 different jobs at the same time that query the analytics cluster, it won't disrupt our ad server because performance in that server is very important. One big thing that it's still haunting us, I guess, is the UTC time zone. When we started, we didn't use UTC time zone. We used Pacific time zone. It was like 7 or 8 years ago, and we didn't envision like having all those fancy pipelines. We were just like, okay, and we built on top of it and on top of it. Now we end up with so many things tied to Pacific time zone, and every time there is daylight saving, it's a pain because you end up either processing the same hour twice or missing 1 hour. Everyone has to wake up at night, and so never use something other than UTC. Always use UTC. It's for your own good.
Or just never grow.
Or just never grow.
If everything's on one server, you're okay.
Also deployment of pipelines can be a bit tricky. When you have a pipeline that runs for an hour and it runs every hour, when you want to deploy a new version of the code, you need to make sure that it completed properly, but you're not interrupting it in the middle, and that there's not like incomplete data, all sort of things. So making sure that your tasks are rerunnable is something very important, because then when you deploy something, you can just interrupt whatever's running right now and redeploy it, and then you don't have to worry about like, oh, is the data partially in there already? Is like something inconsistent or something like this? So this is, I guess, all that relates to scheduling.
So I have this question again, scheduling. So what if, let's say, the job fails in the middle? Like, are the pipelines idempotent, or like?
That's what we try to achieve, right? Idempotent.
Okay.
Yeah. Sometimes it's tough, but yeah. So basically, it helps a lot because especially in AWS, sometimes you cannot start a server. It's very common. And your pipeline will fail for that, or because one Spark node will fail, and then something will happen, and your job will fail. And then what you can configure in data pipeline is automatic retries. So if your pipelines are idempotent, then automatic retries are really easy to do. Just retry it, and doesn't have to worry about making sure the data is already partially there or not.
And like, what's the spec of your EC2 nodes when you spin up for your pipelines? Is it like each EC2 node has 30 GB of RAM, or is it smaller RAM? Like, what's the, like, how do you?
It depends on the kind of logs that we process. We're usually using larger nodes. I think the pipelines that process the most data, they are like on C48XL. So SMP is bigger compute nodes that you can get from Amazon. Memory-wise, I think we try to use most of the memory and leaving a bit of buffer because it's recommended.
Because Spark usually requires a lot of memory, right?
Yeah,
to manage pipelines, it deals with a lot of data,
it does.
shuffling and everything.
Yeah, sometimes you run out of memory and it will fail.
So what's the cluster size? How many?
So we don't have like a fixed cluster size. Every hour we spin up a new cluster and then we shut it down once we're done. So this way we can like rerun like 20 times the same hour like at once, and you just spin up 20 times the same cluster. I think the biggest cluster that we spin up are something like 40 or 25 C4 8XL, and that processes about 3 hours of data. And then we have smaller ones with like ones that are like literally like 3 nodes processing like not that much data. And it depends.
So how do you decide like based on what actually?
That's not automated. I would say like once you notice that there is more data, then you have more nodes.
But you don't know how the data is coming in, right? Because you might be getting like, are you based on what time of the day or?
We don't do that yet. We will hope at some point we could do that, like dynamically adding more instances if you get more volume, but we don't do that.
So in database cluster, you mentioned you have a separate analytics Cassandra cluster. Like how big is that? Like is to deal with this all Spark pipelines?
How big is it?
It's not that big. It's like eight nodes or something.
8 nodes.
Yeah, 6 or 8 nodes.
They're pretty big machines, but it's not.
They're very beefy i3-2XLs, but they're like 6 or 8 nodes.
Okay.
So why are you writing to Redshift again? What is the purpose? Why can't you write S3 and use Spark to do the analytics?
But we need really quick response time, right?
And Redshift is connected to our BI tools and to our internal like dashboards, so you can do SQL queries and get data out of Redshift. And it's much faster than like running like a Spark jobs on S3.
But is it more of who is accessing the data? Is it
So like
analytics team or is more of a customer?
Your BI team and then customers that want to see how many ads were served yesterday, or what's their revenue for the month, or I don't know, where people have served ads, or
So what are the number of concurrent users on that dashboard?
that fluctuates a lot. Concurrent, like at any given, like really it's probably like 5 or 6 queries at a time.
Okay.
It's not like something like 6,000 queries. It doesn't work that way, Redshift.
Yeah, that's what like there are like 15 max on the concurrent requests on Redshift. So
you can configure it, but yeah, I mean it's very low the number of concurrents that you can do. It's not like thousands.
The Cassandra data, is it kept in there for like a 30-day period, or is it like kept in there?
It depends what kind of data. Some visitor data, it expires based on what the partner tells to. I don't know. You're in advertising, so you know like GMPs and all those guys who have different policies. It depends. Sometimes 90 days, sometimes 30 days, sometimes.
Every DMP has its own TTL.
Oh, okay.
We obey that TTL.
Yeah.
Or every partner has its own TTL.
For everything that's like page related, like we also in Cassandra we store metadata about the page or the images, and I think those we keep for 30 days.
So
seven
for images we keep 30 days, and pages we keep 7 days.
So for partition strategies, what kind of partition strategy you guys are using? You're doing the hourly partition, or you're based on customer partition, like using advertiser ID or something. What kind of partition strategy?
in Redshift.
No, for the Spark, for Parquet, and for the data, for your data lake.
So using by partition you mean like the dimensions we use?
Like you're just partitioning and creating Parquet files into just hourly buckets?
Yeah, but the partition key is hourly. I mean,
Hourly.
yeah, hourly.
So time-based kind of.
Time-based. Yeah. Because most queries we have like a time filter in there. Like it's very rare that they ask for like back on 2010 till now.
Okay.
Alright, so let's talk about Redshift maintenance issues that we faced. Even though it's like fully managed, Redshift's maintenance is kind of painful. You can, well, vacuum is mandatory. So as you add more data, you need to sort it and merge it together with existing data. And vacuuming is kind of slowing down your cluster. So that's one very big pain point there. You need to really keep track of the sort ratio and skew ratio of the table and make sure that it's always in a like, acceptable sorted way. I don't know how to phrase that, but basically if you fall behind, then your vacuum is going to have to do much more work, and then it's just going to slow down your cluster for like days or something.
So how frequently you do the vacuuming?
Every night. Every night. We have a script that looks at tables that needs vacuuming, and then based on that it runs the vacuum. Resizing and restoring from backups can take hours, and that's an issue because in Redshift, when you resize or when you restore, it's in read-only mode. So any data that you try to add you need to stop that. I mean, all the pipelines that you have running hourly to add more data to your cluster, you need to stop them. And
What do you mean by resizing in this context?
resizing, meaning if you have like 10 nodes and you need to go like to 20 nodes,
Oh, okay.
then it becomes a really
Scaling your cluster.
Scaling your cluster.
That's
Yeah.
right.
In the Redshift they call it resize.
Oh, okay.
That's why you use resize. Yeah. And also changing the instance type for your Redshift cluster whenever you want to go to a bigger type of node or a different type of node, like more SSD or hard drive based nodes. What we've seen is that it's often easier to restore or snapshot than migrate all the data that's been resize the snapshot to convert it to the new type of node and then move all the data that's been populated since the beginning of your operation. That's much easier than just trying to resize and trying to orchestrate after that all the data that's been inserted, all those things.
So I was just wondering, like putting in Redshift and trying to query it
Yeah.
instead of just put it in S3 and use a Spectrum or Athena to query it. You can do the same thing, right?
It can do the same thing, but it's much faster to have it in a Redshift ready.
Okay.
And the order of magnitude is like 3 to 10. So like you will get like 3 times to 10 times more performance by having it in Redshift itself versus Spectrum.
Redshift's a column or data store,
Yes.
source, so I'm assuming, I'm not familiar at all with Athena. What's it doing?
Athena is similar, like you can query S3 buckets directly.
Okay, but the data isn't organized in
It
a way
basically
to
spins
make
up a
it fast.
Redshift cluster behind the scenes and for you instead of putting in
Oh.
Redshift itself.
I don't think it
Just
uses
abstraction.
Redshift, it uses Presto and Hive.
Yeah,
The back end.
Oh.
Yeah, we
Okay,
basically
that's
have
why it's so
options
much
to do
slower.
Redshift.
Yeah, it basically has to like download the files from S3, read them, like do all sorts of things. Versus Redshift has like strategies to like adding sort keys, distribution keys, like the data is collocated on the same node, so if you join it's quicker. It has all sorts of advantages.
And like working with Redshift, I found that the schema data type is very limited. Is that like you cannot write nested schemas?
Nested is a bit tricky, yeah.
Because when I was writing the analytical queries in Spark, it was very easy. Like it was able to handle with any kind of complex schema.
Yeah.
So is that a limitation in Redshift that complicates your pipeline basically to transform data in multiple ways?
We do have pipelines that like get nested data and like I guess put it in like one layer.
Flatten it out.
Yeah.
Okay.
But I mean, yeah, I guess that's the downside of it. Single points of failure. They claim that, I mean, Amazon claims that it doesn't have any single point of failure, but that's not true. Like if the leader goes down and your cluster is down, or if sometimes also like a regular like worker node goes down, you still can have issues where your entire cluster is down. And sometimes you even have to file a support ticket, and meanwhile all your customers are yelling at you because you can't give them their report in time or things like this.
So what does it mean to you, like when the cluster is down? What happens?
It means that all the tools that we expose to our customers, so they can monitor how much money they're making or how many ads they're serving, all of this is down.
Wow.
And it means also that all the internal people that are using Redshift to monitor the performance of their campaigns, all those guys, they cannot work basically because they are spending their life on those dashboards and making sure that this ad is serving the right demographic on the right sites and all those things.
So how frequently did it happen in the past?
It happens once every 6 months maybe.
Oh, okay.
It's not very often, but when it happens, it's
Yeah,
Everything's at a halt. Your
Yeah.
whole pipeline stops at that.
yeah. Plus all your pipelines are
So
failing.
everything else is
Yeah.
built, it's like the
Right.
hose, clamp down on the hose.
Yeah.
And there's nothing you can do, right? You have to just wait till.
Well, you
Yeah.
can call your technical account manager. And tell him, but yeah, you have to wait.
No, it's good because nobody blames us. Yeah.
I'm more impressed with. Nobody blames you. 'Cause I'm like, I don't care. But Amazon, what? AW who?
So how big is your Redshift cluster then?
It's 14 C, like the
DC2,
DC2
8XLs.
8 or 16, I don't know, the biggest one on the SSD.
So how much Redshift has data? Like you said you have 50 terabytes every day, right?
So no, so we absolutely don't keep that much data in there.
Okay.
It's aggregated data first of all, so it's not like it's like way aggregated, and we also keep only 30 days of data for like reports that really take a lot of space.
So you keep only like 10% of like your data lake in Redshift and like,
oh, much less, I would say.
Less than 10%.
Yeah, everything's already been pre-computed.
Yeah,
small
yeah.
Right.
images.
Good,
So
Each step in that pipeline, Spark, you're narrowing it down.
Yeah.
I assume.
So that means that the platform only needs 10% of data to query at that time. Right?
Sorry.
So you said like platform needs only that much data to query against, right?
Well, since it's aggregated to a point where, yeah, I mean, it's much less data.
Okay.
Yeah. Less than 10%. And we remove data from some reports that are not like, where we don't need like historical data back to like 3 years ago, for example, so we keep cleaning it up. And yeah, that's the. And that's actually when like Redshift Spectrum and things like Athena comes in. Like it means that all this data that we discover, it can be available in Parquet or in Athena.
Right.
Then you can get the data from there if you really need it. Reliably get the log files to S3. So we have like a pretty large cluster of ad servers, and it's about 500 during peak time. And we are all in an auto-scaling group, so meaning at night when the traffic goes down, we end up having like maybe 100 ad servers, and then during the day it's 500. So nodes get turned off and on all the time, and also there is sometimes failure in those nodes, and like pretty much Amazon needs to replace it by another node, or like a hard drive fails or whatever, and then your node will be inaccessible. So you cannot just write into those machines and then periodically upload the files because those nodes keep like going up and down. So for a while we've struggled finding half ago, and Fluentd was maybe 3 years ago. Before, I think we were mostly relying on having like writing to log files and then uploading to S3 periodically, and having like hooks whenever a machine gets shut down to automatically upload to S3, but that was never very reliable, and we were losing about like 1% of data every day. In advertising, it's not that bad to lose 1% of your data, but that was a fact. And now we are like achieving like, I don't know, we're almost not losing any event out of those 100 million. So that's a pretty good improvement there. So as I mentioned, I think it's important for you to have two different ways to get the data from your servers. In case one of the two systems fail, you won't have to worry about like, oh, how am I going to recover this data? How is it going to impact my customers? If your primary pipeline fails, you can just point secondary as your primary source of data, and then that should fix everything. Yeah, making your servers as stateless as possible. As I said, when they come up and down all the time, try not to keep any data on them. This way you don't have to worry about, oh, can I shut it down now? Oh, no, I have to first upload those 3 things, and it's much easier to have it stateless, as stateless as possible, and publish all the data to like something like Kafka or Fluentd, and get it out. The roadmap for this batch pipeline, I would say exploring alternatives to AWS data pipeline. So AWS data pipeline is the tool that we use to schedule everything, right, and orchestrate all those activities. What we've noticed is that they are kind of discontinuing this. I mean, not really discontinuing, but they stop improving it and adding new features. And for example, when Amazon releases a new type of compute or memory instance, it takes 1 year for us to be able to use it in their pipeline. So we're like, well, okay, we're like, up until recently, we were still using C3 instances. And C3, we have been releasing C4 and C5 already. So that's something we don't really like. So we are considering something like Airflow or other like scheduling open source software. Increasing our usage of Redshift Spectrum and Athena. Those two things are pretty recent, and we have still a lot of reports that are not leveraging this to the full extent. So we want to put some effort into this. And serverless is also something that seems to be a focus for Amazon. And they have come up with this new analytics tool called Glue, and that basically lets you run some code without worrying about how many instances you're using, what kind of instances you're using. It's you're just giving your code the data, then they will spin up as many machines as you need. and you will pay just for those machines. So that's something we're also considering.
Did you explore other data tools like BigQuery or anything in your architecture compared to AWS?
We haven't tried BigQuery. I don't know what you mean by data tool. That's kind of
like for analytical queries and everything. Like AWS provides this whole stack, and then GCP provides its own stack. Did you guys ever explore anything?
We didn't try Google Cloud. Yeah. I don't know. I mean, at some point we tried. I mean, a long time ago we had Hive, and we kind of replaced it by Redshift. But no, we haven't made so much effort recently into looking outside of the AWS ecosystem. Sorry. So now I can talk a bit about the real-time pipeline. So it's a bit simpler since this is not necessarily like what produces the actual data that's being used by the customer. It's just temporary data that's being overridden every hour by the batch pipeline. So that's why we don't have like two pipelines and like all these extra safety layers. So it's basically our servers producing the data to the same Kafka cluster in the batch pipeline. Then we're using Storm to get the data out of Kafka, process it, aggregate it, and then everything gets stored into Trade. And the connection between the two is using the Tranquility plugin, which is an open source software that's provided by Trade that integrates nicely with Storm. So as for the pipeline, in terms of topologies, we don't have that many topologies. We have only 7 topologies, 13 data sources in Trade. It's the equivalent of tables. And all those tables, we have like 30 metrics each and 15 dimensions each. But each of those tables are like very massive. Like this is literally like terabytes every day that gets added to those tables. And that's the size of our clusters. Since you guys were asking, I guess that can help a bit. 24 M4 2x large for Kafka, 80 grid nodes, so it's a mix of C5, 4XL and M5 2XL depending on what kind of node it is inside the grid, and 40 C4 4XL for Storm nodes.
Like, have you guys found any difficulty dealing with managing Storm cluster?
I have a slide about that.
Okay.
So let's talk about the real-time issues. One that's very common for all those systems is unbalanced workloads. And what it means is that ending up creating hotspots in your systems, meaning sending more data to one node than another. For Kafka, an example of when this can happen is if you have nodes that have more partitions than others. Usually when you create your topic at first, it distributes them properly. But when a node goes down, or whenever you need to add more partitions and things like this, you can end up in an unbalanced state with some nodes having like 2 times more partitions than other nodes, or also having more leader partition on some nodes than others. And those leader nodes, they are basically getting more traffic, like write traffic to them. So it can create hotspots. So one thing that needs to be done is to monitor partition assignments to those nodes regularly. If you don't do that, then you'll have hotspots, and then you'll wonder why your performance is degrading all of a sudden, why it's not using all the CPU evenly everywhere, things like this. Something similar can happen with Storm when the number of spouts and balls per worker won't be even, and then it's especially more important for spouts, because if you have like 2 spouts on one machine and 1 spout on an hour, then basically the one that has 2 spouts will receive 2 times more traffic than the other one. So that's something you need to keep in mind. Always make sure that you have the same amount of spouts on each of your workers, so they can receive the same amount of data. And for Trade, the real-time ingestion tasks can also become unbalanced because of how Trade assigned the tasks to to its middle managers. Basically, if you have like let's say 10 data sources, and one of them is much larger than another, how Trade assigns tasks for this data source is that it's going to first fill up one middle manager, then go to the next one. So if you create a data source, it's going to fill up the same middle manager with the same data source, and then it will keep going like that. And then if this data source is much larger, then you create a hotspot there again. So you need to dedicate sets of middle managers to data sources and make sure that the tasks for these data sources are evenly distributed across those middle managers. So that's examples of unbalanced workloads with issues that we faced with our real-time pipeline.
So what is it, Druid? What exactly, what is its purpose?
Druid is a database, basically. It's like Redshift, but really geared toward real-time.
Oh.
So in Redshift, I don't know if you use Redshift a lot, but if you try to like get data like as soon as possible to Redshift, it's not doable. It's not going to scale. So Druid, what it does is that you can insert data in Druid, and it will be inserted right away, and you will be able to query it like instantaneously. So basically, from the moment someone serves an ad to us being able to see it in Redshift, in Druid, it takes about like less than 10 seconds.
So it's like this is an on-prem database, or is this in AWS cloud?
It's an open source software, but deployed in our cloud. Yeah. So we're maintaining it ourselves.
Okay.
So, because Redshift has the ability to stream data into it, but you're saying that the performance of streaming data into Redshift isn't that great?
Yeah, it's not great.
Why couldn't you write S3 itself? Again, it's a question.
Well,
what does it add value when you write to Druid? Does it give any relational?
Well, yeah, it's not really relational. Like Druid is not very flexible in terms of what kind of query you can do. But in S3, like let's say you have 100 billion event throughout the day, right? And you want to be able to see every hour, every second your data being refreshed, right?
Mm-hmm.
It means you will need to upload to S3 every second and very tiny files, right? And that the performance of having those very tiny files in S3 will be terrible.
Mm-hmm.
Plus, uploading to S3 is not as quick as pushing data to Druid. This is like geared, like they designed it so it's more real time.
Mm-hmm.
Like yeah.
So is that mostly Druid serving, say, customer reports on?
I don't think it's actually serving customer reports. It's used for internal optimizations.
Okay.
For example, let's say
If you have some data scientist creates a model and it
yeah.
has a feedback based on what's going
exactly.
on there.
So you create an option, you see, like those bits on this website for those keywords, for those, countries, they're getting higher bid, so we're going to raise the bid floor.
Mm-hmm.
So it does that automatically based on the data that it sees in Druid and keeps changing our margin and our bid floors progressively based on the data in there.
Mm-hmm.
And it's also used by our internal teams to see where their ads are being served and all those things in real time, because like they have a dashboard where they can basically launch campaigns, and then instantaneously they can go on this dashboard and see, my ad is serving now, and this is serving at that rate. And they make sure that it's not serving too much or too little on the right places. And all of this needs to happen in real time. Otherwise, we're losing money, basically.
So why did you guys choose Storm instead of like a Spark streaming or Apache Flink? Like, is there a reason behind
I'll also talk about that later, but basically, it was the only one, like back in 2012, right?
2012.
Yeah, it makes sense that time.
And we haven't migrated yet, but it's in the plan. We're planning on going to Spark streaming.
Yeah, stream can give you better control and even smaller packets also, I guess. Yeah.
So here it goes.
Finally, a slide dedicated to Storm.
So, as you said, it's no longer the most popular real-time processing framework. Spark streaming, Flink, Kafka streams also for server-side complex. So yeah, that's one thing. And then, since it's not longer the most popular one, every software that integrates with Storm tends to not release its new version as quickly in terms of operability with Storm. So let's say like Storm version 1.2 comes out, it will take months for having like the Kafka plugin to be compatible with Kafka Storm 1.2. Or Druid is the same thing. They focus on like Spark streaming or things like this. So that's one problem we're facing there. And I think it's also inefficient compared to other technologies from what I've understood, but I haven't run benchmark, so that's only a speculation, but I think that's what it is. And it's also difficult to manage. Like there's Zookeeper in the mix. I hate Zookeeper. And also like Nimbus, and sometimes it's
Yeah.
failed for some reason you don't really understand. You end up on the mailing list from a post from 2010. That's like kind of similar, but not really. It's like it's not a good software.
But you are doing the hard job.
What?
You are doing the hard job.
I guess. Yeah.
So having Kafka and Druid at the end, you can easily swap the Storm with
Yeah.
Flink. Like Druid has those
Yeah.
integrations nicely.
Yes, Druid has
Flink
integration
has
with
fast
Flink,
streaming.
fast streaming.
Do that.
Yeah. Issues network bottleneck. So I think that's not something you see usually in bigger workloads. The network bottleneck. It's more like compute intensive and memory intensive usually, except when you're performing maintenance. So when you perform maintenance, and for example on Kafka, right? If you're trying to reassign partitions, then your network all of a sudden is going to jump like crazy. And if you don't account for that, and if you don't leave extra space to perform those maintenance operations, when it's actually time to do those maintenance operations, then you'll be screwed and you won't be able to do it. And that happened for Kafka. We had uneven partitions, and we tried to reshuffle them and even it out. And what we didn't notice was that the network on those blocks was going to be saturated once we do that. And once you trigger a partition to be reassigned in Kafka, basically it's very difficult to come back from that until it's done. So we had like basically those partitions being reassigned, and at the same time new data flowing in, and the network got saturated, and we had no choice but to like create a new Kafka cluster, change the traffic to that, and then wait for the old Kafka cluster to be back to normal.
So did you use any third-party tools for this uniform distribution of partitions for Kafka, or just use the default Kafka scripts to do
Yeah,
that?
we use the default Kafka script. Okay. Well, actually, yeah. I guess we use the tool that lists the assignments of partitions, and then we reassign them based on what it says evenly. Like we don't really use their tool either because it doesn't really work. But
So are there any tools you're suggesting? Or?
No, means there are some open source projects, right, where they give you the whole reassignment plan and then you just feed it to the Kafka.
But is it reliable, the reassignment plan that they give you?
No, but it's similar. We haven't seen anything big difference between what Kafka also gives you the reassignment plan, right? But we're exploring it, like because maintaining that shuffling and everything is a bit of a pain in Kafka. So I don't know if you guys have used any other tools.
No, we don't. We don't.
They provide that, but
They
we
promise.
charge.
They promise. Yeah.
Yeah, for the content platform.
Yeah.
And one more slide about the piece of software that I dislike.
I like this slide.
Zookeeper. It's in every component of our real-time pipeline. It's in Kafka, it's in Storm, it's in Druid as well, unfortunately. And I mean, sometimes it just fails for some reason, or sometimes even like just Amazon will like have a node failure. And they promise you that it's highly available and all those things, but what we've noticed is that every time a node goes down, then there is some impact on your systems, unfortunately. And then
Zookeeper is mainly configuration, right?
It's configuration and like for example in Druid when a new piece of or a new segment is being published, it will publish it to Zookeeper, and then all nodes will know about it. So it's to like propagate configuration in a way.
Okay, got it. So, all right. So it's basically hooked into the different things for discovery.
Yeah, for discovery, exactly.
Okay,
Discovery
so
and-
it's beyond. All right.
So all those tools they use Zookeeper, and when Zookeeper goes down, then basically you have to do some manual operations. And and what we've noticed also is that people don't really like Zookeeper, so they don't really tend to like go deep into Zookeeper, even though we should have an expert in Zookeeper. So that's something to keep in mind, that if Zookeeper is in your architecture, then try to spend some time trying to understand. A few random tips and tricks for Kafka, Storm, and Druid. Kafka, define your number of partitions carefully, and that's very important because once you create the number of partitions, it's difficult to resize them after that. And one thing we've learned is that you need to pick a number that you can divide in many different ways. And the reason why is because one consumer can only read I mean, one partition can only be read at a time by one consumer, and you cannot split a partition in different consumers. So now let's say you have, or I guess I'll give a different example there. But that's one tip that I'm giving you there. Use a data format that works well for your data. We picked Avro because it works really well with Kafka and the Confluent platform. Confluent provides something called schema registry, where you can publish all your schema about, or all your Avro schema about your data. And then your producers and consumers will, I guess, check with this schema registry and make sure that the data that's being sent to your topic is respecting the schema. So you don't end up sending partial data or incorrect data or things like this. And then you screw up like all your consumers and things like this. So that's pretty much why we use Avro, and also because Avro reduced the data transfer by a lot between all machines.
So there's logging, if it's catching incorrect data, you want to know about that too, right?
Yeah, I mean, yeah, it will throw an exception in your code basically, saying, hey, like, this is not compatible with your schema. So that's how you learn about it. And make sure to monitor the network in and out and scale proactively, so you don't end up in those situations I described.
So you guys are not managing your in-house own Kafka, like you are using Confluent Kafka?
No, we're using the open source version provided by Confluent, so we are managing it.
Okay.
We're not paying them to manage it or anything.
Okay.
Their pricing is pretty ridiculous.
Yeah, I talked to them.
Yeah, I talked to them at reInvent, and it's pretty crazy. Storm, always keep one extra Storm supervisor idle, so it can pick up the work in case of failure. That's one thing that Storm does well. When one node in your topology goes down, it will automatically reassign the worker that was on that node to a different node. This way, if something happens during the night, no one has to wake up and you can just fix the node in the morning. That's one thing that's good. So here comes the example about the Kafka partitions. You need to think carefully about the partition, number of partition and number of spouts, because you can have only one consumer per partition, basically. And what happens is that if, for example, you're not picking a number that you can divide easily, then when it's time to scale, then you basically have to recreate the topic with more partitions. So that's why it's easier if you pick a number like 60, for example, then you can have 10 consumers, or you can have 15 consumers, you can have 20 consumers, 30 consumers. So every time you have like incremental steps that you can take to scale your cluster. If you have 50, then it's only 10, 25, and then 50 consumers that you can have at the same time. So that's why it's important to get something that you can divide by many different numbers, so it allows you to scale progressively. And it's also important to understand that spouts only can read from different number of partitions, but every single one of those partitions will give you the same amount of data, right? And if you don't have, if one worker has more partitions than another, then you're creating hotspots. So that's why it's a good rule of thumb, this. And one also advice, if you're using Storm, that's like very simple to do. What it does usually is that it sends data from a spout to another bolt, and keeps going like that as a topology, as its name says, I guess. And what you want to do is avoid having to go from a spout in node A to a bolt in node B, because then you have to serialize the data, send it over the network, and then deserialize it. So this configuration, what it does is, when possible, it will serialize send the data out of the spout to the bolt that's on the same worker as your spout. So you don't have to serialize and deserialize, and you don't have to send across the network. And that's like huge performance improvements for literally just changing, I think, shuffle grouping to local or shuffle grouping. That's like all you have to do, and you improve your performance by crazy amounts. So that's for Druid. In Druid, there's a cool thing called cold and hot storage that lets you assign different types of nodes for different period in your data. So let's say most of your data gets access for the last 30 days. Then you can have like a really big, like beefy cluster for serving those last 30 days. And then if the data for like the past year doesn't get used that much, then you can use smaller instances with bigger disks to host this data. And then you can configure all those policies based on what type of query you get to your on your cluster. Make sure the data flows evenly across your real-time tasks. So that's what I was mentioning earlier with the issues we faced. And use Pivot. So Pivot is like an open source tool that comes with Drill. And basically, you get a jar, I think, or some zip. You unzip it, you point your Drill cluster at it, and it will discover all of this for you. All your dimensions, all your measures, and all those things. And it will let you plot graphs like this with group bys, filters, all sorts of things like this. So that's, for example, like a quick example of tracking that we're giving or something. And yeah, that's out of the box. So that's like a free thing that you get with Drill, and that's pretty amazing, I think. The roadmap for real time, as we said, like move to another real-time framework, processing framework, Spark Streaming most probably. And why Spark Streaming? What we've been seeing is that people use GPUs more and more, and people have started using GPU for big data applications as well. And we've met with a company that's based in Santa Monica actually, called fastdata.io. And what they promised us is that this big Storm cluster that we have, they can reduce it to like 1 or 2 instances using GPU. So the cost saving there is huge. And what they say is that they have an API that's fully compatible with Spark Streaming. So that's why Spark Streaming, I think if we go towards Spark Streaming, then we'll be able to easily test the thing and see if actually like using GPUs can improve our processing time like, by that much. Like it's like by 10 times. And then, I mean, that's like maybe way in the future is to have not get rid of the batch pipeline and just have a real-time pipeline that's reliable enough for making it like the primary source of data without having to worry about correcting the data every hour. Right now it's not really the case because we have a lot of failures in those real-time pipelines. Sometimes like the data gets delayed a bit and all those things. So that's why we don't feel comfortable yet as like making the real-time pipeline the like source of truth.
Have you looked into Apache Apex?
No.
Okay.
But I've heard of it.
Yeah, we had OC Jug. We had them down, and you know, it was it came out I guess around the time of Storm. The thing was that it was a company called Data Torrent, and it was proprietary, and they were showing things. I think they showed it to the Twitter guys, and like, this is awesome, but we have a policy of never using any proprietary software. So they finally, you know, at some point did that, but I think it looked like it. I mean, from the numbers they're showing, it could handle way more. Like they were talking about, like kind of like early IoT, where, like power companies, you know, where you have all these homes doing all this, you know, data, and it sounded very powerful.
Yeah, I thought it's amazing, but I've never like been remotely looking.
I would say it's worth taking a look.
All right, thanks for the insight.
So in your pipelines, how are you handling deduping and everything? Like you have to code in each of your pipeline the deduping logic, or you are like, how are you managing?
We're not so worried about deduping, to be honest. Like in Redshift, we have a unique ID for every event. So we have a script that periodically checks if something is duplicated. Usually we don't have any duplication, or we have we tolerate like a certain like threshold of duplicate data. I mean, if you work in advertising, you probably know that like those numbers anyway they get verified by third parties, and there's anyway like 10% discrepancy with those third parties. So if you have like 0.001% of duplicates, that's not very important. So that's why we made the trade-off of like not worrying too much about it, making things simpler.
You said so you're fastdata.io for the GPU processor.
Yeah.
Is that just for number crunching, or is that for like machine learning?
It's for the exact same thing you will do for like our use case of like processing logs, aggregating them together, and then pushing it to S3 or something.
Okay.
So the exact it's compatible with Spark basically. So
yeah.
But I think it supports mlib too.
Oh, okay.
So everything that Spark does, they can do it.
Okay.
Yeah, I don't know exactly how they do it or what they do exactly, but
Yeah.
Then when you
that's
Spark
what we promised.
side.
And I want to talk also a bit about operational challenges. We're almost there again. basically when you have hundreds of different reports and like 70 plus pipelines, with each pipeline having like dozens of activities, create this report, send this email, create this alert, all those things. It can become quite challenging to make sure that all those activities are running properly. So what I would really strongly advise is having a tool to make sure that every activity that you expect to run is actually being run and on time. So there's like a bunch of open source software that you can use for that. And then that's something that we've added like surprisingly not so long ago, and that's like made us discover so many issues. Because sometimes like someone make you create a new report that gets seen once every 3 months, and then it fails in the middle, and then you forgot to add like the proper monitoring for it. And then 3 months later, when he checks the report, he's like, "Hey, where's my data?" And you're like, "Oh, it's been failing for the past 3 months." So that's one important thing I would say. Have a script ready to rerun activities in bulk. And if you're in AWS, it's even more important because sometimes you have like AZ-wide outages, region-wide outages. And when this happens, they can be done for like several hours. It happens like once a year, maybe or twice a year. But when it happens, then for like maybe 3, 4, 5 hours, none of your activities will get done. And then when your engineers have to like make sure that everything ran properly and everything is in order, then if you have to do that manually, then they're going to be there for like, I don't know, 2 days making sure everything works. So be ready with those scripts to rerun activities, to rerun jobs, to rerun everything in bulk, so your engineers can just click 3 buttons and it's done. And then make every process rerunnable. So I guess that's the idempotency we mentioned. That helps a lot with having a lot of moving pieces, because you don't want to investigate every single piece in there. You just rerun from the beginning. It will execute all those steps, and then not worrying about changing things.
So for monitoring, did you guys use CloudWatch or any other tool for monitoring all the pipelines and everything?
Monitoring, so there's a mix. There is AWS Data Pipeline provides like an integration with CloudWatch and SNS. So it can trigger those 2 alerts. SNS is linked on our end to PagerDuty. So depending on what kind of error it is, it can trigger like a call on our phone. We also send emails. We have scripts that run periodically to compare data, to make sure the data is there, to make sure everything looks correct. And then for the pipelines, that's pretty much it. I think for the clusters, we use Ganglia and CloudWatch. And probably other monitoring tools. I don't remember all them all. So let's talk about the AWS bill. I mean, when you have that many instances, like it can become quite crazy. So what we've noticed is that some people might start clusters because we let them start clusters to test or whatever. Then they forget about this cluster, and this cluster can cost you like $1,000 a day, right? So when you realize like 30 days later that you've been spending all this money all this time, then you're like, oh, well, how do I avoid that, right? So what we've done is we've enforced owner tags.
Charge the employees.
Yeah, right.
That quick.
So with the owner tag, what it does is that if you create a cluster and you don't provide your email address, then it will send an email to an entire engineer saying, hey, this cluster is not tagged, and then you can make sure that, okay, it will get tagged properly. And you can also send a report every day to someone saying, hey, you still have this cluster running. So that's, I guess, the 2 things we've done to make sure people don't forget those clusters. So basically, if you've been running this 30-node cluster, you will receive an email every day saying, hey, do you still need this 30-node cluster or not? And you can also send it to your hosting if you really need to. So they can keep a watch on that.
So what's the average monthly cost on AWS?
$600,000.
I don't know if it's a lot, but that seems a lot to me. Make sure to establish a current billing tag policy, so that's similar to that one tag. Every piece of your system need to be properly tagged with a billing that says, okay, this is what it does. So you can monitor the cost of this thing, especially if you have like letting all your employees control how many instances are used for that, like for example, our pipeline, as I was saying, like it depends. When you see that you need more data, you have more data, then you add more instances. So this way you can really make sure that, hey, like, I'm not gonna all of a sudden double the amount of money that I'm spending on like Spark or on trade or on whatever. So it's important, and checking that weekly. And being aware of network costs is also very important in big data applications. Costs between machines in AWS. I mean, there is a cost for network between machines in AWS when they are across AZs. And in all those software like Kafka, Storm, whatever, they always recommend to deploy it in multiple availability zone for like high reliability and all those things. But then everything gets replicated across those boxes, and you spend like hundreds of thousands of dollars on that. So if your data is not that critical and that you can tolerate having Kafka going down, or you can tolerate having like Storm going down, then just put all your nodes into the same AZ. And then, well, if the AZ goes down like once a year, well, that will be down, but it's only real-time data, it doesn't matter that much. But you will save like a lot of money by doing that, not having those network transfer across AZ.
So all your 50 terabytes data every day that you get is stored in S3, like every day?
Yes.
Okay, so it's like S3, your S3 has petabytes of data.
Yes.
Correct.
So you don't have any in-house data lake, so because like it will be very expensive, right, to store everything.
Glacierize, one.
We spend, well, yeah, we use Glacier. At some point we send it to Glacier.
You don't have to put in S3
Yeah.
all the time.
Like it's expensive, but it's not like unmanageable. I would say.
It's about $50,000 a month.
Mm-hmm.
50 to 60, $70,000 a month.
So that's the
And last, addressing production issues. So failures and bugs happen all the time. So my advice is auto-remediate as much as possible. And auto-remediate means try to automate fixing the issues that you might encounter. Meaning if, let's say, a job fails and there is a very common step to fix it, then try to automate that. Or it can be as simple as rerunning the task. Like a lot of times when you're in a cloud environment, you can have a trouble getting an instance because we run out of that instance type at that time or whatever. Very often, just rerunning the activity will fix it. So you don't need to wake up at night, just make sure that everything is rerunnable and rerun it automatically. And at last, put as much information as possible in your alerts. If you have an alert saying, hey, like there's discrepancy between those two data sources, try to put what type of discrepancy it is, like where it's coming from, is it a particular website, is it a particular ad, all those things. So people don't have to like wake up at night and be like, okay, there's a discrepancy, logging into like some analytics tool, figuring it out, doing queries and investigating for like 30 minutes. They can just look at the email, like, oh, that must be because of that, and go there and fix it right away. And that's it for me. So as we said, we're hiring lead data engineer to basically do whatever I presented, right? That seems good to you guys. Software engineer for doing mostly backend, Java, Spring, all those things. And there's other positions that you can look on.
You didn't put DevOps engineer there? Come on!
It's not my team, eh?
It's not my problem.
So what programming languages you use to implement this entire stack?
Java, Scala, and Groovy.
Groovy. So you don't use anything Python in this or?
No data science yet, so maybe.
Not in that.
Okay.
Groovy is kind of a replacement for Python. Like it's very similar, you can do the same kind of stuff. Except you can do all the Java libraries you use for your usual code, you can use them in Groovy. So that's what's very convenient.
Like I saw that that Scala is very concise to write, especially Spark pipelines and everything. But if you try to write in Java, it's like pain. It's
So that's why we use Scala. We use Scala for Spark applications mostly.
Okay.
With Druid, is that similar to a Cassandra database, or is that
Not really. Like Druid is for like time-based data, like basically like
Time series.
time series data. Right? Cassandra is more like key value store.
Yeah.
Druid is actually meant for warehouse.
Okay.
So there's a concept of dimensions and metrics.
Got it.
So it is exactly meant for that.
Okay.
Yeah.
And it's especially geared towards real time.
What are you using Cassandra for? I mean, I was talking with, we had Matt Engines from from Couchbase and, you know, it's competitor. But, you know, I've heard from